So, the sheet you have in front of you, there is going to be 4 questions tomorrow on your multiple choice section of your test that involves photoelectron spectroscopy. Spectroscopy. I can't say that word ever, okay? So, sounds painful. But remember we talked about the photoelectric effect in the very beginning of the notes when we said that if you take light, if you take a photon of light and you hit it on a metal surface at a high enough energy, then it will make the electron bounce off. Okay? So, when we make those electrons bounce off, we get the ionization energy. Remember, ionization energy is the amount of energy it takes to remove an electron. Okay, so in this case, we're talking about how much energy does it take to move them off. And what we get is a graph like this, and we call this photoelectron spectroscopy, or just call it PES for short, which works out a lot better for all of us involved. Okay, so here's your graph. What does this graph mean? So we're going to start by reading. Okay, so the boxes are there just for you to fill in. Note that the y-axis shows the relative number of electrons in each peak, okay? So here's your y-axis, relative number of electrons. So this peak is going to have a certain number. So this peak will have a certain number, and it's going to have the same number as this peak. How do I know that? Because they're the same height. And so I know this peak should have more or less electrons. More, okay? This peak should have the same number of electrons as the first two, right? Do we see that? So the peaks tell me the relative number of electrons. The peak heights, therefore, show how many electrons would have a given ionization energy relative to another peak. Recall that the closer an electron is to the nucleus, the more energy would be needed to remove that electron from an atom. So in the diagram above, the peak at 349 represents electrons closest to the nucleus, right? Because if we're more attracted to the nucleus, it's going to take more energy to remove, correct? In the first shell, we know from electron configuration that 2 electrons can fit into the 1s sublevel. So we can surmise that the peak at 349 represents 2 1s electrons. So we would say this is the 1s2 sublevel on that first peak. Do we see that? Okay. So each peak represents a sublevel. Okay. Each peak on here represents a sublevel. So we know it's going to take the most energy to remove the electrons that are the closest to the nucleus, correct? Yes? All right. So, which electrons are closest to the nucleus? 1s2. So I know since this one requires the most energy, we're going from 347 to almost 0 down here. Okay? Since this one requires the most energy, that must be the 1s2. Okay? All right. The next peak at 37.1 megajoules per mole would represent electrons in the what shell? 2s shell. Note that the height of this peak is the same as the height of the first peak, so the peak should represent how many electrons? 2. So what sublevel should this be? 2s with a configuration of 2s2. So we would say this one is 2s2. You following me so far? No, the next peak at 29.1 megajoules per mole should be what electrons? What comes after 2s? 2p, right? Note how large this peak is compared to the prior peak. The peak at 29.1 megajoules per mole represents 2p6, right? Everybody agree with that? And how do I know it's full, that all 6 of them are there? Because it keeps going, right? If there's peaks after it, then it means that that peak must have been full. The peak at 3.93 megajoules per mole represents 3s electrons, because after 2p comes 3s. The peak at 2.38 megajoules per mole represents the 3p6 electrons. Note, the height of this peak is the same as the height for the 6 2p electrons at 29.1 megajoules per mole, so I know this must be 3p6. The last peak at 0.42 megajoules per mole would be for electrons in the 4s sublevel, right? Based on the height of this peak, the number of electrons is 1, because the height of the peak is 1/2 the height of the peaks at 3.93, 37.1, and 349. Does everybody see that? How I know there's only 1 electron there instead of 2? Because it's half the height, which means it has half the number of electrons. So if I ask you what element this was on the periodic table, what would you tell me? It would be potassium, because potassium ends in 4s1.
So will they use this like to show how?
Like this would be a free response kind of thing, or would it be?
This is going to be multiple choice.
So it'd be like, hey,
That's
what
easy.
element
You
is
just gotta
this?
keep going down.
Or you can
Okay.
just look at the end.
Yeah.
So, this is what they're going to look like on your test. And you don't have this in front of you. This is just on my smartboard. Okay? So this is what it's going to look like on the test. Your x-axis is still ionization energy. Your y-axis is still relative number of electrons. What's the difference? Instead of it all being on one line, notice here how they show these squiggly marks there? That means there was a big jump. Notice we're at 347, 345. All of a sudden we took a jump to 37. And then here we took a jump to from 29 to 4. What did they do here instead of making it big
They
jumps?
showed the whole thing.
Just different, right?
They just did it on 3 different lines. They went from 500 to 100, and then from 100 to 10, and then from 10 to 0. Do we see that?
So 390 would be like
So 390 has to represent what?
1.
1s2, right?
So this is calcium.
Okay. This one represents,
2s2.
and then this one is, this would be,
3s2.
this would be
4. 4 and then
P6.
no, 3
3p6, and then this would be 4s2. So what element is this? Calcium.
It's easy.
Not too hard.
We see this? Pretty easy, right? Okay. There's going to be, again, I'll say it, 1, 2, 3, 4 multiple choice questions based off of these.
This one you read like
Yes. Okay. Everybody got this? We feel comfortable with this? So we're not going to freak out when we see this tomorrow in our test. We're going to get excited because you know that's easy points, right?
How many questions are on the test?
30 multiple choice. And then you're going to do 1 long, 2 short for your response questions.
Are we doing it by ourselves or in group?
By yourself. Yeah, yes. All right, let's take out your free response sheet that you got last Thursday while the seniors were taking the exam. Were you not here last Thursday? You were in here with me.
I know, but I was in there literally. I don't remember if I came back in here. I know I came back in here, but I'm not.
I handed them out before y'all left. You
I
should
know,
have
I
it.
think like 30 minutes early.
Yeah.
Everybody in this class period should have it because you didn't go to Stokes. You stayed with me.
Did you, have those extra periodic tables printed out?
All right, number one, we're going to get as far as we can get in this class period. If we don't finish, or if you still have more questions after we get finished today, I set an alarm on my phone that says you cannot hit snooze study session this morning, okay? So that way I won't hit snooze tomorrow, and the latest I will be here is at 7:10, period. Okay? So if you still have questions after this, I'll be here tomorrow morning at 7:10. Well, I always check my phone, like my alarm will go off and I'll see what time it is to see if I can hit snooze or not. So now the message will pop up, you cannot hit snooze. Can't do it. You got to get up. All right. Number 1A says write the ground state electron configuration for an arsenic atom showing the number of electrons in each subshell. So electron configuration is letters and numbers. Okay? So you didn't have to draw the arrows, you just had to do your letters and your numbers. So arsenic is AS on the periodic table. It is number 33. So I look at that and I know I should end with what?
AS.
4P3, right? So now I can just go through and fill it in. What comes first? 1s2, then
2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p3.
excellent. And that's what you should have written.
We can't do we're getting a row all gone and then.
I wouldn't have in this case because it's short. Show what you know. Make them proud. Okay. Okay. So B says give one permissible set of 4 quantum numbers for each of the outermost electrons in a single arsenic atom when it is in its ground state. Where are my outermost electrons coming from? 4p3 and 4s2.
Oh, yeah.
Okay, remember when we do quantum numbers, either N, L, M, S. Remember N is your principal quantum number and it lets me know the distance from the nucleus. Okay, now this is where I feel like I must have done a bad job explaining because I confused third period really bad, so I take full responsibility for this. Okay, so I'm going to need you to make sure you are paying attention to the next few things I say. All right, just because 4s fills in before 3d, it does not mean that 4s is closer to the nucleus. It is not. Okay, your principal quantum number, N, tells you distance from the nucleus. The principal quantum number for anything in 4s is going to be what? 4. Your principal quantum number for anything in 3d is going to be what? 3. What's closer to the nucleus, 3 or 4? 3. 3d is closer to the nucleus, okay? 4s is just lower in energy, okay? Why is 4s, even though it's technically further from the nucleus, lower in energy than 3d? What did we talk about? S is less than P, which is less than D, which is less than F. Why? Because S penetrates the nucleus more. S stands a greater chance of penetrating the nucleus, which means even though 3 is technically closer to the nucleus, 3d10, those 4s2 electrons stand a greater chance of getting the closest to the nucleus because they stand the greatest chance of penetrating the nucleus. Does that make sense? which means since they stand a greater chance of getting closer, it makes them in a lower energy. Okay? Now, does it mean when they first feel that they are closer to the nucleus than 3D? No, they're not. Okay? They're just in a lower energy. Does this make sense? Okay? It really does? Okay. So I don't want you to get confused by that. Okay? They fill in according to energies. Okay? Not how close they are to the nucleus. All right? You good? So the first electrons that would be removed here would be the what? 4p's, right? Then what would be the second group of electrons to be removed? The 4s. Then what would be the third group of electrons to be removed? 3d. Then 3p, then 3s, then 2p, then 2s, then 1s. Does that make sense? Okay. So my outermost electrons here are my 4s and my 4p. We good with that? Okay. So to do the quantum numbers, the easiest thing to do is to draw them. So I would say, well, my 4s is up, down, because it's full. And then my 4p is just up, 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 right? All right. So the S level, what are my quantum numbers going to be for it? Let's just do the first arrow first. It's going to be, what's N going to be? 4. L is 0. M is 0. And S is positive 1/2, right? Because it's an up arrow. And then the next one would be
Same thing except for just one.
4, 0, 0, and then a negative 1/2, right? Everybody got that? So then my p orbital, let's start with the first one and then work our way down. What's N going to be? 4. L's going to be? M's going to be? Negative 1. And S is going to be? Positive 1/2. Next we would have 4, 1, 0, positive 1/2. And then next we would have 4, 1, 1, positive 1/2. Got that? C. Is an isolated arsenic atom in the ground state paramagnetic or diamagnetic? Explain briefly.
Well, if it's in a ground state, wouldn't it mean that, like, if it has like 1s2, would that mean that they're already paired? Or like,
Ground state means it's this.
yeah, it's paramagnetic.
It's paramagnetic. Why is it paramagnetic?
It has one or more unpaired electrons.
There you go. Because it has how many unpaired electrons?
3.
3, right? And so that would be my explanation. Is paramagnetic? It has 3 unpaired electrons.
So if it's diamagnetic, 4p2.
If it was diamagnetic, everything would be paired. There would be 0 unpaired electrons. Diamagnetic just means everything is paired.
So if there's any unpaired.
If there's any unpaired electrons, it's paramagnetic.
But you would write whatever number it is.
I would just write how many unpaired electrons it has to show that I know magnetism depends on the paired electrons. Okay. Everybody got that? We feel good about this one? I didn't confuse the mess out of us? All right, good. Yes. Kinda, yeah. That's what this is for. These are old free response questions. So, no. All right. Number 2. 2 important concepts that relate the behavior of electrons in atom systems are the Heisenberg uncertainty principle and the wave-particle duality of matter. A says state the Heisenberg uncertainty principle as it is related to determining the position and the momentum of an object. What do we know about the Heisenberg uncertainty principle?
If you want to define the momentum of an electron, you have to forego knowledge of its exact position at the time of the measurement.
Excellent. It is impossible to know the momentum and the position of an electron in an atom at the same time. Okay. So if I know position, that means I have to give up knowing the momentum. Or if I know the momentum, that means I have to give up knowing the position. I can't know both of them at the same time. Okay? That's literally all it means. Okay. B says what aspect of the Bohr theory of the atom is considered unsatisfactory as a result of the Heisenberg uncertainty principle. And we didn't talk about this a lot, so I'll just go ahead and tell you that. The Bohr theory said that the electron in a hydrogen atom traveled in a fixed orbit with a fixed momentum. So, how does that violate the Heisenberg uncertainty principle?
Because they're not fixed. They're always moving. You can't know both of them.
There you go. If it's a fixed orbit with a fixed momentum, can I know the position and the momentum at the same time? Yes. Okay. So that's how it violates the principle. Because if we go by that, then we could say, well, then in a hydrogen atom, I can know the position and the momentum. All right, C. Don't stress about C. Okay.
Trust me, I won't.
All right. Don't stress about C. I'm going to go over it right quick, but you don't have to stress about this one at all. Okay. In fact, I would prefer you to not stress about it at all. So, yeah, just please don't. Yeah, I mean, yeah, don't really stress about anything. Okay. All right. So, C says explain why the uncertainty principle or the wave nature of particles is not significant when describing the behavior of macroscopic objects, but it is very significant when describing the behavior of electrons. We did this equation in class. Remember we talked about this. We said that all matter, okay? Remember we talked about the wave-particle duality of matter. All matter behaves as a wave and a particle. Okay, but when I throw a baseball, do I see the wavelength of that baseball? Okay, do I see the baseball moving up and down, up and down, up and down, up and down? When I throw it regularly, I'm not talking about a designed pitch. Okay, all right. I knew it was coming because his wheels were turning. All right, do I see that? No. Okay, or a better example, so Zach can't come up with a. No. All right, is if a truck driving down the highway, do I see the truck moving as a wave? No, you don't, okay, because it's a macroscopic object, okay? Whereas if I looked at the orbit of an electron, okay, or if I look at light, I can see the light behaving in waves if I look at the particles, the photons of light. They move in waves. So it's saying, why is it significant? Like small objects, I can see the wavelength, whereas with large objects, I can't. And that's because of this equation that says wavelength is equal to Planck's constant, okay, divided by mass times my frequency. Okay, Well, this is the equation. So let's look at it. If I have a really large mass, okay, that's gamma. That stands for wavelength. Okay. If I have a really large mass, what happens to this number right here? It just becomes really, really small, right? Okay. So that means, can I see how my wavelength is affected? No, I can't at all. Whereas if my mass is very, very small, what happens to this number?
So, like,
It's large enough to see how my wavelength is affected, right? Do we see that? Okay. So that's why with microscopic objects you can see it, and with macroscopics you can't. You with me? We're good? Don't stress over that one, okay? If you got A and B, I'm good. 3. Answer the following questions regarding light and its interactions with molecules, atoms, and ions. A says the longest wavelength of light with enough energy to break the chlorine-chlorine bond in Cl2 is 495 nanometers. Number 1 says calculate the frequency in seconds to the negative 1 of the light. What equation am I using here?
C equals wavelength times.
C equals wavelength times frequency, right? What am I solving for here? Frequency. So I would say, all right, so that means frequency is equal to what?
C over wavelength.
C over wavelength. C is a constant. What is the speed of light?
3.0 times 10 to the 8th. Is that given to us or meters per
3.0 times 10 to the 8th meters per second. That's on your AP equation sheet. As is the equation. They're both on there. Divided by, since this is in meters per second, what do I have to convert my nanometers to? Meters. How many meters are in 1 nanometer? 1 times 10 to the, what's nano sound like? 9. So we do it times 10 to the negative 9th. So then if I get that, I know that my frequency is 6.06 times 10 to the 14th. Seconds to the negative 1. And you could put hertz. Well, they told you the unit there. They said to do it in seconds to the negative 1. So it was kind of given to you already. And they did that on all of these.
So it would be wrong to put what we put hertz and then gave us seconds to the negative 1.
No, I don't think they would count it wrong.
I'm probably just going to do the same, but I don't think that.
All right, the second thing says calculate the energy in joules of a photon of the light. What equation am I using for this? E equals HV, where the H is, what's H stand for? What do we call H? Planck's constant.
Yeah.
Okay, Planck's constant, which is 6.626 times 10 to the negative 34 joules times second. Yeah.
Is that an arc equation?
Yes, it is.
Miss Nellie,
Yes, ma'am.
would you send Bella Sanders to the office and she'll be back?
Yes, ma'am.
Thank you.
No problem. Times. Do we have the frequency?
Yeah, we just found it.
We just found the frequency, right? It's 6.06 times 10 to the 14th seconds to the negative 1. So that means my seconds do what? Cancel. So now I'm left with joules, which is what they asked me to find it in, correct? Yes. So if I multiplied that out, I would get 4.02 times 10 to the negative 19 joules. Is that me or somebody else? Who's your- All right. And then this last one, don't worry about this because we haven't gotten to this yet. I didn't realize it when I put it on your study guide, or I would have taken it off of there. So it said, calculate the minimum energy in kilojoules per moles to the -1 of the chlorine-chlorine bond. So what I'm wanting to know is how many kilojoules per mole. Okay? So I say, all right, well, I've got how much energy have I already calculated? 4.02 times 10 to the -19th joules, right? Okay. They want kilojoules per mole, okay? Well, I know in 1 mole, they put mole to the -1, so that means moles has to be on the what? Bottom, okay? How many atoms do I know is in every mole?
So
6.02 times 10 to the 23rd, right? Avogadro's number? Correct? Flashbacks. Okay. So now I've got joules per what? Mole, but they asked me to put it in what? Kilojoules per mole. So I would say in 1 joule, there's how many kilojoules? 0.001, right? Yes? Remember? Kilo, hecto, deca. There's my base. So I would go back 1, 2, 3. So there's 0.001 kilojoules in a joule. So then what do you get for your answer? You should get 2.42 times 10 to the... Somebody help me out here.
Is it to the second or to the negative?
Let me see. Oh, okay. So did you just get 242?
Yes, that's what I
Alright.
got.
So you should have got 242 kilojoules per mole.
How do you know to like use frequency or like that? What do you use a little 4.02? How do you like measure that?
How did I know to use what?
Like the 4.02, the energy. How do you know?
Because I calculated how much energy was in the photon of light that was required to break the bond. So then it said, so what's the minimum energy that's in that bond? Okay. So it said the longest wavelength of light with enough energy is 495. Okay. So I found the frequency, which then helped me find the energy that that photon must have had. So how much energy is in that bond in kilojoules per mole? So this is how much energy is in the bond, but it wants it per mole. So I say, okay, well, there's 6.02 times 10 to the 23rd of those in 1 mole, right? Okay, and then to get it from kilojoules to joules, I just did that conversion. Does that make sense? We got that? Number 4, a certain line in the spectrum of atomic hydrogen is associated with the electronic transition in the hydrogen atom from the 6th energy level to the 2nd energy level. Number 1 says indicate whether the hydrogen atom emits energy or whether it absorbs energy during the transition. Justify your answer.
I think that it emits.
It does emit energy. That's what you should have put.
Because it's losing energy as it moves from energy level 6 to energy level 2.
There you go. That's good. N equals 6 is a higher energy level than N equals 2, right? So if I go from high energy to low energy, that means I had to what?
You feel like let energy
I had to let energy go, right? So I had to emit the energy. Does that make sense? And that's really all you had to put for that one. Yay? Yay? Yay. Everybody got it? I know I didn't write a lot on that, but you didn't have to write a lot. So. All right, number 5. Here we go. The diagram shows the first ionization energies for the elements from lithium to neon. briefly in 1 to 3 sentences. Remember those synthesis writings where you had to answer in 3 sentences or less? That means no matter what I write in my answer, I'm going to make sure that it's 3 sentences or less. Okay? Explain each of the following in terms of atomic structure. Okay? So, A says, in general, there is an increase in the first ionization energy from lithium to neon. So they're saying in general. Now, did they increase the whole way up? No, there's a couple of places where it dips. But are they asking me to explain the anomalies yet? No. They're just asking me to explain the general trend. So I look on my periodic table. I see lithium, I see neon. To get from lithium to neon, what did I do? I had to go across. So what is my argument that I'm going to use if I have to go across? Effective nuclear charge. Okay? So, I say, A, as you move across the periodic table, now I'm abbreviating and I'm shorthanding, you would write in complete sentences. Yes, you would, right? Right, okay. As you move across the periodic table, okay, the effective nuclear charge is what? Is increasing as the nucleus becomes more what? Okay. This causes the electrons to be more what? To be more attracted to the nucleus, which means my ionization energy is going to what? Increasing, or increases. I didn't even use proper grammar there. Yes? Is that not the same argument we used 1,000 times in class? Make sure we use it. Now, B and C are now asking me to explain why it dropped between beryllium and boron and why it dropped between nitrogen and oxygen. So now they're asking me to explain the exceptions to the rule. Okay. Now normally I told you on the AP exam, if they ask you for an exception, explain the general trend first. But we already just did that in what? A. So would I restate everything again? No. Okay. So A, I explained the general trend. Now B, they want me to explain why is the first ionization energy of boron lower than the first ionization energy of beryllium?
Because boron is in the p orbital and beryllium is in the s orbital, and s penetrates the electron cloud, so they're held tighter by attraction, not p is held cloud, and is therefore not held tightly by attraction, so it's easier for boron to.
That is correct. Okay, what she said was correct. Let's Let's see if we can shorten this a little bit. And you wouldn't have to write the configurations on the test, but if you get stuck, you can write the electron configuration, right, to help you out. So I say, okay, so beryllium is 1s2, 2s2, and I see that boron is 1s2, 2s2, 2p1. Now, can that just be my explanation? No. Okay? And in fact, they're not even going to care that you wrote down the electron configuration. That's more for your benefit. And it's honestly something I would probably just kind of like do to the side and then write my explanation. Okay? So, I would say, all right, so the electron being removed the electron being removed from beryllium is a 2s electron, while the electron being removed from boron is a 2p electron. Two p electrons are higher in energy because there is less penetration of the nucleus. Therefore, the electrons are easier to remove. Everybody got that? All right, let's go to C. The first ionization energy of oxygen is lower than that of nitrogen. So even though oxygen's effective nuclear charge is greater, it still has a lower ionization energy. Okay? The first thing I would do is off to the side somewhere, I would write out the electron configuration, so hopefully I could understand what was going on. And I say, oxygen is 2p4, which means it has a paired, whereas nitrogen is only 2p3, so therefore does not have any paired electrons. So then I would write that, okay? I would write the electron being ionized in oxygen is paired with another electron. Whereas the electron being removed in nitrogen is in a singly occupied orbital. And you wouldn't have to word it exactly the way I just worded it there, but it is good if you now know it to do it. Okay? Notice how I wrote about oxygen and I wrote about nitrogen, because they're asking me to compare the two of them, so therefore I need to write something about both of them, right? In language with Powell and Elrod. Okay? If you're comparing two things, do you not have to write about both things? Yes. You got to write about both things. Okay? So, the ionization energy of oxygen is less because oxygen is trying to what?
Minimize electron efficient.
There you go. Because of the electron repulsion. D. I know. It gets long. It gets tedious. But your test is tomorrow, and you're going to be glad we did this tomorrow. Like, really glad. Like, really, really
So
glad.
you think we got it on the system?
I'm looking for really good test grades, and I'm really excited about it.
I feel like
I wouldn't look for results.
Don't look my way.
Okay? No, you're not.
Last one was really easy.
This one's going to be great. I'm excited.
I would say that too.
Yeah.
I need a good day, you know?
There we go.
That's all I would say.
There you go. I like it, Hope. I like it a lot. All right, D says predict how the first ionization energy of sodium is going to compare to lithium and to neon. Explain. What do I notice about sodium compared to lithium and neon? Lithium and neon's outermost electrons are in what energy level? 2, right? Lithiums are in 2s, neons are in 2p, so they're both in energy level 2, whereas sodium's ionization energy is coming from what? The third energy level, right? Okay. So the electron in sodium is going to be
Further out.
further from the nucleus, so therefore it's going to be easier to remove, right? Because it's further away from the nucleus? Yes?
Yeah.
We agree with that? Do I need to write this out?
Yes. Is that energy lower?
Huh?
Is that measured energy lower?
Yes. So I would say the ionization energy of sodium is going to be less than lithium and neon. The electron being removed from sodium comes from the 3s orbital, which is further from the nucleus and less tightly held. Alright, so that's what I would go with for D. If you have questions about the last question, number 6, then you can come see me tomorrow. Okay? Alright. Hopefully I'll see you this afternoon.